This video will give you a brief introduction of a one-way ANOVA. So a one-way ANOVA is considered a single-factor design in that you only have one factor or one independent variable that's establishing your groups within an ANOVA. And so when we look at it, you just have this one independent variable, and this one independent variable is establishing your J levels, treatments, treatment levels. All of these are just different terms to discuss your groups that are being established and are being compared. Then, just like every single ANOVA, regardless if it has one factor or multiple, you have your dependent variable, which is your outcome variable. And you have to remember that this is a continuous variable, and it's your outcome. And so this is what's giving you the mean that is being compared across your groups. This dependent variable needs to be continuous so that you do have a mean calculation, but that you also have a proper variance calculation as well. The null hypothesis for these single factor designs or one-way ANOVAs is all about the quality of the means. So are the means equal? And this will be very similar to all of your ANOVA designs, because ANOVA is that comparison of means across groups. And so we want to look at the null hypothesis, so when nothing happens, as that all of the means are equal, that when we compare them, there is no difference between those means. And when we say there's no difference between those means, we really mean that statistically, there is no difference. So you can have means in groups that are different, but it's not a statistically significant ANOVA. And so that is accepting the null hypothesis that these means are essentially equivalent. And so then our alternate hypothesis is that not all the means are equal. But what you need to pay attention to is that this does not mean that all of the means are different. And it doesn't mean that all of them are the same. It really just means that there is a significant difference between at least two of the means that are included in your ANOVA. So if you have three groups, at least two of those means need to be statistically significant in their difference between those means to get a statistically significant ANOVA. But without doing further analyses, you're not going to be able to know where those differences occur. There are some additional ANOVA terms that you just should be aware of. So as you are conducting one-way ANOVAs and really any of these ANOVA designs, these are some of the terms that you should be using and you should know. So the first is the main effect. So the main effect is, are there differences between the means of the groups? And remembering that there only has to be a difference or statistical difference between two groups for there to be a statistically significant ANOVA. You also should know the mean square values, where that's those ratio of the sum of squares, where you have the sum of squares divided by the degrees of freedom, and you have it for total, for between, and for within. There should be some discussion about these mean square values when you're discussing your ANOVA results. Should also be aware that whenever we say factor, we are talking about the independent variable that is establishing the levels. These levels are the groups. These are also sometimes called the treatments or the treatment levels. And also another really important term for ANOVA in particular is effect size, where effect size is looking at how big of a difference is there between these different groups, and is this difference between the means practical in our application of the results. So this is our practical significance. So we can get statistical significance to let us know that our main effect is statistically significant, where we do have at least two group means that are found to be statistically different. But our effect size is really our practical significance and tells us, is it practical to apply these results? So are those means different enough to make it make sense to use one treatment over another, to use one program over another, or to be able to say that one group truly is doing better or worse than the other. And so there's several of these effect sizes that we use. We use eta squared and we use omega squared. And these are really based off of the sum of squares, and still using that variance to be able to assess how big of a difference there is. And there are very different thoughts about what effect size to use. So you usually have to go to your industry and look at the literature that is being produced within your topic area or within your industry and use similar effect size calculations. This also comes into how this mean squared value is presented, where there are a lot of different terms for your mean squared value. So we typically see between and within when you're learning about ANOVA, but then when you get into the research field, you'll see some of these others. And so this S and A, this is between, error is within, W is within, and error is also within. So it's just being aware that these are not new mean squared values, but they're just using different subscript terms. So even within a single factor one-way ANOVA design, there are some differences in the designs that could be used. So you could have a between subjects design, a within subjects design, and you can switch up which of your effects are fixed, so you fix them to a term, and which are random, where they're left to be calculated based off of your data. So you just have to be aware of what type of one-way ANOVA design is being used. And so for any of these one-way ANOVAs, you have your equation here where your Y is your observed score. So it's looking at your observed score equals this population mean, which is what we're striving for, and is usually calculated based off of the expected values. And you have the effect being in the group. So this is like the between mean differences. So if there's a different mean or a different effect, when you're in a particular group, that's where this value goes. And then you also are looking at the individual random error. So it's the individual's value, so their actual score, versus the expected score. And this is where you get this error term. You should be aware that this looks very similar to a regression equation, because regression and ANOVA are very similar, and they use a lot of the same computations and a lot of the same statistics to be able to examine the variance and the variance changes between variables.